Hi, I am María Soledad Arriaga, and from the Matemática, UAM Iztapalapa, where I am studying my PhD under supervision of Naid Javier and Ilan Goldfeder. And I will talk about alternating Hamiltonian cycles in two-edge colored multigraphs. Okay, the problem of determining the existence of alternating Hamiltonian paths and cycles in two-edge colored multigraphs is an NP-complete problem. Most results on this existence concern on complete and bipartite complete multigraphs, and a few ones on multigraphs with high monochromatic degrees or regular monochromatic subgraphs. But in this case, I will talk about a different approach given by Alejandro Balbuena, Hortensia Galeana, and Ilan Goldfeder, who obtained results on this topic by imposing local conditions on the multigraphs and digraphs. For this purpose, I will review some basic concepts and define some new ones. Okay, the basics. As we know, a graph G is a pair of sets B and E, where B is a non-empty finite set with elements called vertices, and E is a finite set with elements called edges that are pairs of these vertices. It's usual to make drawings to represent the graphs by putting dots for vertices and lines for the edges. There exist several classes of graphs, and I will talk about two of them. The classes of edge-colored graphs with color in their edges, and the class of digraphs. In this class, instead of lines, we put arrows between two vertices, and we use D instead of G and A instead of E. A is a set of ordered pairs of vertices. Also, I want to say that a multigraph is a graph where we admit more than one edge between two vertices. Okay, recall that a path in a graph is a sequence of distinct vertices, B1 to Bk, where every pair of consecutive vertices is an edge from G of G, like this or this. If we add the condition that also there's an edge between the first and the last vertex of the sequence, we have a cycle, like these cycles. And when a path visits all the vertices of G, we have we call it Hamiltonian path, like this, I think, or Q, B, C, E, A, T. And similarly, if cycle visits all the vertices of G, we call it Hamiltonian cycle. Okay. Another definition is this. A cycle factor is a collection of mutually vertex disjoint cycles that covers all vertices, like this one. This is a cycle, and we have here another cycle. They are vertex disjoint, and together covers all the vertices. So this is a cycle factor with two cycles. Now we have definitions about digraphs. Okay, first, a tournament T is a digraph for which there exists exactly one arc between each pair of vertices. Then a digraph T is quasi-transitive if for U, B, and W vertices of D, we have that U and W are adjacent whenever we have the arcs UB and BW. So if you have UB, BW, then you must have one arc or WU or UW. And finally, it is a local tournament if U and U are adjacent, again in one way or another. Whenever or we have the arcs UB and WB, or we have the arcs BU, BW. Okay, now definitions about two-edge colored graphs, multigraphs. Given a G two-edge colored multigraph, we say that G is 2M closed if for every monochromatic two-path UBW, monochromatic, we have that U and W are adjacent. It doesn't matter the color, but this edge, it has to be. And similarly, we define that G is a 2M closed multigraph if for every non-monochromatic two-path, UBW, now non-monochromatic, it changes the color. U and W are adjacent. Again, it doesn't matter the color. Another one, given a two-edge colored multigraph G, an alternating Hamiltonian cycle is a Hamiltonian cycle. Remember, a cycle who visits all the vertices such that no two consecutive edges have the same color, like this: red, blue, red, blue, red, blue, red, etc. And finally, color connected. We say that G is a two-edge colored multigraph color connected if for every pair of vertices X and Y in G, there exist two XY paths, P and Q, such that their first edges have different color and also their last edges have different color. Previous at the next concept, new concept, I need this little bit notation. Let G be a two-edge colored multigraph. An edge of G with vertices X and Y, we will denote it by bracket X, Y. And the color of this edge with C of the edge. Okay, now we can do this definition. Let G be a two-edge colored multigraph given two alternating cycles, C1 and C2, and an edge between them, Xi, Yj, we say that C1 and C2 are appropriately left with respect to this edge whenever this path is monochromatic with the color of this edge, obviously. So now results. Proposition 1. Let C1 and C2 both alternating cycles. Okay, if there exist two edges, one in C1 and the other one in C2, such that either this cycle is monochromatic or this cycle is monochromatic, then there exists an alternating cycle with vertex set, the vertices of C1 and the vertices of C2. Okay, like this. In this case, we say that C1 and C2 merge in one cycle. Okay, another result, lemma 2. Let C1 and C2, both alternating cycles, appropriately labeled in a 2H colored and 2M closed multigraph. Then either they merge in one cycle like before, or we have these edges and the color of these ones is different, and so on. Now more definitions. Let C be a cycle in G. We denote by IC the set of vertices with odd subscript, and similarly by PC, P sub C, the set of vertices with even subscript. Even. And with this, we can define color domination between two alternating cycles. We say that C1 blue dominates C2 if the next conditions hold. First, XY is an edge of G for every AX in C and every Y in C1. I'm sorry, for every X in C1 and every Y in C2. And the induced of IC1, the induced by IC1 and the induced by BC1 are completed graphs. The induced by this are completed, and also the induced by this. And all the edges in the induced by IC1, IC1 are blue. All the edges in the induced by BC1 are red. And all the edges between IC1 and C2 are blue. And all the edges between PC1 and PC1 and C2 are red. So if we have all these conditions, we say that C1 blue dominates C2. And we write like this. Similarly, we define C1 red dominates C2. Now we have another result. Let C1 and C2 both alternating cycles in a 2H colored and 2M closed and connected multigraph G. Then either they merge in one cycle, like this, or one of them color dominates the other one. Okay. And now we are ready for the main result. Let it be a 2M closed and color connected multigraph. If it has an alternating cycle factor C with cycle C1 to Cl, then it has an alternating Hamiltonian cycle. And I will do the sketch of the proof of this result. Okay. First, suppose that we can take a minimum cycle factor S from C, with cycle C1 to Cr. Then define a colored digraph D star GS, for short D star, such that their vertices is S. Okay? I'm sorry, the cycles of S. And CICJ is an arc of D star if and only if Ci color dominates Cj. Then prove that D star has no cycles and that if we have, and that for all Ci, Cj, Ck in a vertices of S of D star, if we have the arc CICJ and the arc CICK, then both arcs are have the same color. And with this, proof that D star is a local tournament and D star is a quasi-transitive digraph. And so D star is a tournament, but it has a vertex with all its arcs colored by the same color. But this is a contradiction with the fact that G is color connected. So that this means that L is equal to 1. So G has a Hamiltonian cycle. And that's it. The stock was taken by this article, and thank you.